Hello, and today we are going to be talking about the math behind the problem of a cylinder rolling down an incline. Now, the math for this involves quite a bit of physics to solve, and I will say the credit for the physics in this video goes to Wired.com. They have an article called "A Rolling Object Accelerates Down an Incline" that goes a lot more in depth into this than I do. And that's where I went to for the physics in this video. So, first of all, to solve this problem, we have an incline here. And this incline has a height h and a hypotenuse, let's call it s. Now, the first thing you're going to need to do to solve this problem, as you might guess, is let's actually go and find these values. When you go and measure it out, s turns out to equal 65 inches. And the height h here equals 9.5, also inches. And for this problem, we have a cylinder that starts at the very top here, and we want to find out how long does it take to get to the very bottom. Using our mathematical skills, I'm going to label a couple things here. Cylinder of radius r and a mass m. That'll come up later. And we're seeing how long it takes for it to go down this incline right here. Now, the main equation we're going to be using to solve this is we need to figure out the average velocity of the system, because the average velocity, one of the definitions for it, is V average equals delta S over delta T. And delta S in this equation is talking about how far the cylinder travels. And in this equation, delta x is what I meant, right? Delta x is going to be the distance that's traveled, which is the hypotenuse s. So delta x over t actually equals s over delta t. And that's really useful to us because the only variable we need to figure out is velocity average now. And once we have that, we can solve for this system and find out what t is. Okay. So for this, the first thing you'll need to know here is the moment of inertia, and I won't go into the math behind it, but because we know that this is rolling down a slope, we can say that the moment of inertia for this system, I, there's just an I there, equals 1/2 the mass times the radius squared. So the inertia going down equals 1/2 this radius times the mass of the cylinder. Okay. Now that we know this, we have to talk about the forces acting upon this system. And there are three forces in particular that are acting upon this system. And we need to talk about all of them to see what the total force of the system is. So, first of all, we have the gravitational force that's acting upon the system. And that is actually 0 for this equation when we're talking about the work that the gravitational force does. The reason for that is because that's actually part of the system, since we're talking about the cylinder rolling down an incline. So for gravitational force, we have 0. Next, we have to talk about the normal force. And the normal force is the force of the ramp pushing against the cylinder as it rolls up. So the normal force would look something like this, pushing up. And we're going to find out that that also comes out to be 0. And the reason for that is because the equation for normal force is the work done by it equals the force times delta R times cosine of theta. And in this instance, theta is the angle between these two lines right here, which is going to be 90 degrees. Well, cosine of 90 degrees is 0, so this whole equation here is going to come out to 0. And lastly, we need to talk about the frictional force, which surprisingly is also 0 for this system. The reason for that is if we had a box, let's say, I'll draw a box here to help illustrate that. If we had a box sliding down here, there would be a frictional force going on at the bottom of this box right here as it slid down. But because there's no one point for it to act upon in a cylinder, because as it rolls down, you have a new point and another new point as it goes down and down, we actually don't have a frictional force acting upon any individual point. So this is also going to be 0. And this is important to know. We're going to talk about why in just a bit. But first, we're going to talk about the work-energy equation that we can get from this with some physics that I will certainly not get into right now. And the work-energy equation which is going to equal 0, is 1/2 the mass times the velocity squared, actually velocity 2 squared, which would be the velocity at this point right here, plus 1/2 times the inertia times the angular momentum, we'll talk about that in a minute as well, squared, minus mgh. Now, the reasons that we talked about the forces that are acting upon this system is because we can learn a couple things. First of all, we can say definitively that we know the moment of inertia for this system, which is going to be important for the equation. And secondly, because we know that there isn't a frictional force acting upon it, we can actually figure out what this is as well. And for this equation, I'll write this up here, just have some equations here that we can reference later. The angular force is going to equal, or the angular speed, I should say, is going to equal V over R, and that R is the radius of the cylinder. Right here, or there. Okay, now that we have this, we can start inputting things into this equation and start solving it. So, 0 equals 1/2 the mass times velocity 2 squared, plus 1/2 times 1/2 mass radius squared, since we're inputting this for I, times the angular momentum, angular speed, which is V over R squared, minus mgh. Now, since we have all this in, we can start solving it out, and let's start simplifying this. This equals 1/2 the mass times velocity 2 squared, plus 1/2 times 1/2, 1/4 mass times radius squared times v2 squared over r squared minus mgh. Now, because we have an r squared here and an r squared here, we can just cancel these terms, and we are left with 1/2 mass times velocity 2 squared plus 1/4 mass times velocity 2 squared minus mgh. And you might notice here that we have like terms, so we can combine these as well, and the equation can get much simpler. So this equals 3/4 mass times velocity 2 squared minus mgh. And let's move that mgh to the other side of the equation just for simplicity's sake. So this whole thing equals 3/4 mv squared equals mgh. Now, the variable we need to solve for here is v2, because we're trying to find the average velocity. So, solving for v2, we can cancel these m's out here, and we can multiply by the reciprocal for 4/3. So we get v2 squared equals 4/3 gh. So, when we take the square root of that on both sides, we are going to be left with v2 all by itself equals the square root of 4/3 over the gravitational pull on this system times the height h. You might notice interestingly here that we have completely eliminated from this equation both r and m. And that's significant because the velocity of the cylinder going down here, we have found out, is completely independent of both the mass and the radius. So you can have any size cylinder and you can have any mass cylinder. The velocity going down at the final point will still be the same. So, and you can go test that if you like to verify that. From here, we have a solution for v2. Now, to actually put that into use, we need to talk about velocity average first, because the one definition we gave for velocity average, as you might remember, is s, the distance it's traveled, over t, the time it's traveled. And another definition for velocity average that you'll also see is v average equals v1 plus v2 over 2. And you might be thinking that we don't have a V1 here, but we do know what V1 is, because a V1 is 0, since this thing did not start with a velocity. The cylinder was just resting at first. So V1 equals 0, and since we could put a 0 in there, we get V2 over 2 equals the velocity average. And now we can set that equal to S over delta T. Now this is important because now we can isolate delta T finally and get that all by itself, so we can figure out what it is. Multiplying by delta T on both sides of the equation, we are left with delta T times V2 over 2 equals S. And now let's multiply by the reciprocal here, so 2 over V2 times 2 over V2, and we are left with delta T equals 2S over V2. Now let's plug in what we know for V2 down here. So we are left with delta T equals 2S over the square root of 4/3 GH. Now we have everything set up. The only thing we have left to do is actually plug in the numbers that we have found for all of these values. So delta T equals 2, and we said that this was 65 inches for S right here. So 2 times 65 over the square root of 4/3 times the gravitational pull, and that's 9.81 meters. When you convert that to inches, that comes out to 386.09 inches per second, because it's gravitational pull, times the height, which is 9.5. And once we plug all of that into our calculator, we have 2 times 65 is 130, 386.09 times 9.5 times 4 over 3, square root of which is equal to 69.9. Now we just need to take the numerator, divide it by the denominator here, and we are left with 1.8590 seconds, about. Which is pretty close to what we found from experimentation. And we ended with about 1.952 seconds, about that, for how long it actually took the cylinder to roll down. And we can say a lot of the difference between this 1.859, which is very close, and that 1.952 comes from the friction that you experience in the cylinder, because we aren't in a perfect system, as well as just the lag it takes and, well, human error, things like that. There are plenty of other factors that can contribute as well. But this is how you figure out mathematically, in a perfect system, how long it takes to travel, a cylinder to travel down an incline.